Again, today we're gonna go over the thermodynamics section of the GFEs, specifically the subject 183002, basic energy concepts. And in this one, we just go over basically pressure reducing valve, convergent nozzle, heat exchanger, Rankine cycle, and Mollier diagram. This is only, let me see, 4 questions. So I will just jump right over into the problems. Well, we are now on the section 183002. So let's go over this just 4 questions that we're giving here. The first question that we are giving is this one, question P7769, and it's telling us for which of the following ideal processes, if any, is the steam inlet enthalpy equal to the steam outlet enthalpy. So it's talking about an isenthalpic process here. Inlet enthalpy is equal to outlet enthalpy. So which one of these two will be? Okay, so first we need to understand, okay, what's a pressure reducing valve? Let's go over what a pressure reducing valve is. So a pressure reducing valve or a water pressure regulator, it's a piece of plumbing. We can use it in plumbing or in other places to basically reduce the water. So for example, if we have a house and then we have, water coming, from the city, well, the pressure is going to be very high here, so we need a pressure reducing valve to be able to reduce the pressure going into our homes, right? We don't want this high pressure getting into our homes. So that's why that's one of the uses that we have for this one, this type of valves, like, for day-to-day life. So this type of valve, they have something called a throttling process. And a throttling process, it means basically that this part of the valve, we can have it like, 50% open or 60% open, 80% open. We are throttling the valve. We are like either closing it or opening it at a certain percentage, not completely. So that's kind of like what it means. And a throttling process is an isenthalpic process. So this throttling process is a thermodynamic process in which enthalpy of the gas or the medium remains constant. Right? When we have a throttling thing, something that we can throttle, we are gonna keep our enthalpy constant. And that already by itself is giving us an indication on the answer, right? for this question. So we know that this throttling process have a constant enthalpy. Okay. So during this throttling process, there's no work done by or on the system, and usually there is no heat transfer, meaning there is adiabatic from or into the system as well. So also the throttling process cannot be isentropic, and it is fundamentally irreversible process. Just remember characteristics of this throttling process: no work transfer, no heat transfer. It's irreversible and is isenthalpic. Okay, so the throttling of the flow is going to cause a significant reduction in pressure because a throttling device causes a local pressure loss. So basically, throttling can be achieved simply by introducing a restriction into a line through which a liquid flows. So here, let's say we have it completely open, we're going to throttling, so we're going to start putting a restriction into the flow that goes through here or through here. So that's basically what it's doing. So that's what we're going to have. And from experience, we can observe that the pressure inlet is going to be greater than the pressure outlet. Also, the velocity inlet is going to be smaller than the velocity outlet. So, I'm sorry, the specific volume, not the velocity. So the specific volume is going to be smaller than the specific volume out. And also we can observe that the enthalpies are going to remain the same, and this is because of this formula. So this specific enthalpy is equal to the specific internal energy of the system plus the product of the pressure and the specific volume, right? So if one goes up and the other one goes down, that means that they stay the same. This one remains unaffected and the enthalpy remains constant. And that's basically how it works. But we also have the information on regards to the convergent nozzle. So for the convergent nozzle, we're gonna start it basically like pressure here. The area here gets bigger and then this area gets smaller. So we have a permanent restriction here, right? In this side. So what's gonna happen is that as the fluid enters the smaller cross section, it has to speed up, right? So this part has to speed up in order to conserve energy. So to maintain a constant amount of fluid moving through the restricted portion of the nozzle, this fluid is moving faster in this part, right? So that means that this remains constant, this remains constant, pressure lowers, and that means that the enthalpy is gonna lower as well. So that's why this question, the answer is gonna be only A. So now, let's take a look at this one. Okay, for this one, question P7779, refer to the drawing of a 6-inch diameter pipe containing subcooled water flowing from left to right at 100 gallons per minute. So I only know that I have water flowing from here through here. And that's kind of like an important thing. The speed or the gallons per minute, that doesn't matter. It can be anything. So the pipe is frictionless and no heat transfer, meaning that it is isentropic. And point B is 10 feet higher in elevation than point A. That's something important. So point A and point B, they have a difference in the elevation. As I mentioned, this is something that we need to remember. This is gonna be important here. So we're gonna use basically, we have the same formula, we wanna use it, but we are giving also this information. So we're also gonna have this formula, we're gonna have this Bernoulli kind of equation in here, right? Where we have the kinetic energy, potential energy, right? And also we're gonna have our enthalpy. So we need to determine which one is going up and down. So for this part, we know that the only thing that we are changing here, so we are changing here the elevation. This is one of the things that we are changing on both sides, right? So we have the elevation that is changing in here. So, and in this here, we are also changing the enthalpy, because if we change, for instance, the potential energy, we increase the potential energy, we know that the enthalpy has to go down. And that's how we are going to be able to conserve, have this conservation of mass here. Right? We are only just changing the elevation. But let's take a look at the answers here. So he's asking us, how does the enthalpy of the water from point A to point B compare? So in the first one, he's telling us that the enthalpy of the water at point A is smaller because some of the water's kinetic energy is converted to enthalpy as it flows from point B. We are not converting kinetic energy at all in here, so that's not going to be our answer. So now, the enthalpy of the water from point A is greater because some of the water enthalpy is converted to potential energy as it flows from point B. So yeah, I mean, we have that enthalpy is going to be converted to potential energy. So the enthalpy at point A, in this point here, we have it in here, is higher, right? It's going to be higher. So we will say that this one is right. Let's take a look at the other one. So the other one is this. It states that the enthalpy of the water from point A and B is the same, and that is not true. I mean, we'll have to have a trolling process here. We're not having a trolling process. So no, this cannot be the same because that means that H1 is equal to H2, and that's not true because we don't have a trolling process here, right? So now D says the enthalpy of the water at point A and B is the same. Well, we already determined that that's not true, right? And it says because the total energy of the water does not change from point A and B. Even though that's true, we know that the water from point A and B is not true. And that's how kind of like we can analyze or answer a little bit. So now let's go to the next one. The next one is going to be, we're going to be talking about a convergent nozzle, and we're going to be talking about a heat exchanger. So for this one, for the convergent nozzle, we already talked about the convergent nozzle, but we haven't talked about the heat exchanger. So a heat exchanger is a device in which energy is transferred from one fluid to another across a solid surface, and one liquid is going to be hotter than the other, and the energy transfer is going to be from hotter to colder, right? That's kind of like how it works. So for this one, we're going to have this convergent nozzle, and we're going to have this heat exchanger, and this is asking, so we have a fluid, it's asking for which of the following processes, if any, is the fluid outlet enthalpy greater than the fluid of inlet enthalpy. Inlet enthalpy is smaller than the outlet enthalpy. Okay. But here, remember what we determined from the convergent nozzle. We have this one being greater than this one. So if we remember, we already know that A is not going to be the answer, right? So we just need to kind of like analyze this other one. So for this one, the only things that, we are changing is going to be our temperature. So that means that we're only affecting our internal energy. So if we are increasing our temperature, that means we're increasing our enthalpy because our specific volume and pressure are the same. In this case, we're not affecting this part of the equation. So that's why the inlet enthalpy is going to be smaller than the outlet enthalpy. And that's why Bravo is going to be our answer in this case. Now, we're going to have this other question here. This is kind of like I approach it. So we're going to have the parameters from the question P7809 is telling us, given the following steam parameters, we have pressure 1000 psia and quality 90%. It's asking us the specific enthalpy of the steam will be greater if the pressure of the steam was 100 psia at the same quality, or if the quality of the steam was 100% at the same pressure. So this is like giving us like options. It's giving like options to think about. This one is telling us, okay, so let's say that the pressure of the steam, which right now it's 1,000. If it was 100 psi lower, meaning it can be 900 or higher, right? And he's telling us, okay, the steam quality is 98%. If the steam quality is either 97 or 99, it's either higher or lower, right? It's giving us the option of higher or lower. And we want to get what will give us the greatest enthalpy. And for that, we really need to use our Mollier diagram. So for the Mollier diagram, we have 1,000 psi here. This is where we are at 98. So this is our point. So the only way to have a higher enthalpy is going up here a little bit, is increasing our quality. We can increase our quality at the same pressure. So that's one of the things we can increase our quality at same pressure. So we can go that way. And that will increase our enthalpy because the enthalpy is going to be in this side. So instead of being here, we're going to be here. We're going to be a little up. Instead of being just here, we are here, right? So these are my options. The other option is decreasing my pressure. So if I decrease my pressure and increase my quality, that can also allow me to have a higher enthalpy. I will be in the highest part here. So one of the options will be increase the quality and decrease the pressure, right? Increase the quality and decrease the pressure. Let's see if we have that. So if the PSIA or if the pressure was 100 PSIA lower and the steam quality was 1% higher, and yeah, that's our answer. That's what's gonna give us the highest or the greatest enthalpy in here. So specific enthalpy of the steam will be greater. So yeah, that answer will give us the greater enthalpy. But this is kind of like we have to analyze a little bit. This is not the original steam diagram that we use for GFEs. The other one is clearer. It looks better. I feel like this type of thing will be better explained in person. But yeah, this is kind of like, this is an example of how you can approach this problem. And that's gonna be it for this section. Thank you.